So the first thing I look at in this problem, since they're asking for an entropy change, there's only one equation that works with that. Um, First and foremost, let's look at what the problem gave us. They're asking us to ignore all heat transfer. We are dealing with ideal gases, and we're looking at a volume change where we have an expansion. And of course, it's an isothermal expansion in this case. So maybe I should write down isothermal process. We'll put that into the mix. So the only ideal gas problem that we see, or the ideal gas equation that we see, is ds equaling to dq over t. And during the expansion, perhaps q does change. So what we're going to do is we want to find ds, but we know that we run into trouble right away because we don't have t nor dq. So right away, we are being pushed into a side quest. Our side quest is to figure out what dq is. Okay, I'm seeing dq, I'm seeing the word isothermal process, I see expansion with v's, and I'm thinking v is a work thing. I mean, there's a work function that has v's in it. It's isothermal, which means that the change in temperature is zero, so the change in internal energy is zero. Automatically, I'm just thinking of this equation right here. The change in internal energy, or I guess thermal energy, is the change in, or the Q and the work that's being done or by the system. So if something is isothermal, then dE is zero. That's what isothermal means. Isothermal means there's no change in temperature, so therefore the energy of the system remains the same through the expansion process. If that's the case, then we see that dq becomes a function of dw, which is basically just negative dw. And we also know one thing, dw is work, right? Work is simply pressure dv. Again, this is just another relationship that we know from our notes. Okay, so we have two relationships. The energy relationship, this is in a way the first law of thermodynamics. And the second relationship is linking work with pressure and volume. This is actually the same as relating work to force times distance. It's just in a different format. So now we see that dq is equal to negative p dv. And then so voila, we might have a dq on our hands. Here's the problem. We know what dv is because that's in a way given to us. We know v changes, so we can safely say that we probably know what dv is. We don't know what the pressure is. Well, that's terrible. So what we need to do now is go on to a side quest. Okay, now we're going to go deeper into the rabbit's hole here and do a second side quest. Well, the second side quest, we know that this is an ideal gas. So pressure has to relate to volume and temperature somehow. Well, we just use the ideal gas law, and maybe this can enlighten us with a few things. Well, we don't know what pressure is, obviously, but we do know that we have, n moles, because that's in the problem, and moles are expanding. We have the ideal gas constant. We don't have T, but we do have the particular volume in which the pressure relies on. Now, the problem is I would say we have a side quest because we don't know what a T is, but we need to find out what a P is. The good news is we have a T here. So I'm thinking that maybe these two T's will cancel out. So what I'm going to do is I'm going to go ahead and go back up the rabbit hole. We're going to go from side quest to side quest, insert the formula, and then go back to our original problem and just kind of see where we're at. We'll reanalyze and we'll take another side quest if we need to. So ds is equal to dq over t. Now, dq is negative p dv, and P is simply given from the ideal gas law. So plugging all this in, we have negative N R T over V dV divided by T. Okay, this is great because look at what I'm seeing here. The T's are actually going to cancel out and we can just put V on the bottom. So this actually ends up being negative N R over V, and then we'll put a dV off to the side. Okay, this is actually starting to look good. We know what N is. We know what R is. We have a V function at least, and we're going to go ahead and just plug in the appropriate values when we do the integration, and we have dV. So this automatically is a good equation because we do have a V. This is a check mark, by the way. We do have a V, and we are integrating with respect to that same parameter. So now we're going to go ahead and take an integral from an entropy change of 0 to S, depending on how V changes, and V goes from, it looks like V1 to V2. Let's go ahead and solve this out. So the change in entropy, we're going to go ahead and just say change in entropy from S to 0. I'm sorry, this doesn't go from 0 to S. It just goes from S1 to S2, which then ends up being the change in entropy anyways, which is what we're trying to figure out. That's going to equal to negative NR integral of dV over V, and that's simply equal to negative NR natural log of V from V1 to V2. Now, from previous problems, we probably already know that if we take a natural log of V, where we go from V1 to V2, that's going to equal to natural log of V2 minus the natural log of V1. And the law of logs here is that if you have a log function minus or plus another log function, it then becomes a division or multiplication of the argument. So instead of natural log V2 minus natural log V1, we have natural log V2 divided by V1. And this actually ends up being our answer for the change in entropy delta S. Your part A is complete with that equation. Now, go ahead and write part A here. For part B, all they ask you to do is to write in the values. You got 1 mole and you have a relationship between V2 and V1. Okay, so writing this equation, we have, instead of N, now we have 1 mole. We have 8.31, and I believe the unit for that is joules per mole K, but let me verify. Okay, so verified, yes, it's going to be joules per mole K. And we have natural log of V2 over V1, but in this case, they say V2 is twice that of V1. So this ends up being 2 V1 divided by V1. The V1s obviously cancel out, leaving a 2 in the argument of the natural log. If you all put this into your calculator, you're going to get the final change in entropy to be negative 5.76 joules per Kelvin. And that's going to be your answer as you expand. So what's interestingly enough is that you can analyze it. If you're doing a thermal expansion, the temperature is going to go down, and that's just going to give you a negative or a decrease in entropy because there are fewer ways for the molecules to arrange themselves in these plethora of microstates. So in a way, if you have, lowering temperature and or decreasing volume, you're going to essentially get a lowering of the number of macro states, and that's going to give you lower entropy in general. But I think the general takeaway is that lowering the temperature does decrease entropy in general.